Hello and welcome. I'm Russ Edwards. I'm a subject matter expert with Award Solutions, a senior consultant here, and I'm also leading the Technology for Business series that helps those in sales and business-related roles understand and speak the language of technology a bit better. Today we are going to be talking about QoS in LTE, and this is the first part of a multi-part series because, as you can imagine, there's a lot involved in this particular topic. And so this first session is going to be dealing with QoS, the definition of QoS. We're going to be understanding what is QoS, and we're not going to define it as it's defined in a lot of different ways in different parts of the industry. We're really going to zoom in on the cellular industry, and we're going to talk about key elements of QoS that are really relevant to the cellular industry. So let's go ahead and get started here. Now, in order to understand QoS, it's helpful to understand how current cellular networks treat our traffic. And so typically, if this is the cellular network, of course, it can't be a network without being a cloud, right? So if this is the cellular network, data comes in to the cellular network from websites or whatever we happen to be talking to. It could be our enterprise that we are connected to. And it comes out the cellular network to the device. And this data could be any sort of traffic. We could have web page traffic that's coming down. We could maybe we're using Vonage or Skype or something and doing voice over IP. So some of these IP packets could be voice over IP packets. Maybe we're doing some sort of streaming video, and we could have streaming video packets. Of course, we need more of those, right? Maybe we're doing some sort of a file download. All right, so currently, the cellular network handles this traffic in what we call a best effort, with a best effort approach. And what this means is it's sort of a first in, first come, first serve type of approach. And the cellular network says, if data comes in, I'll do my best to try to get it out to you in a timely manner. But this works a fair amount, and you may have even tried using some sort of voice over IP over a cellular network, and you had reasonable results with it. So it can work as long as the network is not facing a lot of competing demands simultaneously. But if the network becomes more congested, or if there's more going on in the network, and the network now can't get everything out as fast as it needs to be pushed through the network, then we could start to experience some service degradation. And that's where the topic of quality of service comes in. So in a network that supports quality of service, the cellular network now receives these packets and, in essence, treats these as distinct streams of information. So I have my video that the cellular network realizes this is video and it's different from a file transfer, and I need to treat it as such. Maybe if I'm doing the voice over IP, it's a separate stream of information and is recognized by the network as being a separate stream so that we can treat it differently. Okay, so that's where we're going with this, and where we're going with LTE is that we're trying to get to a point where the network really does treat these different streams of information differently. All right, so if we want to define QoS, QoS stems, we need to understand this first point. And that says that different services have different requirements. Okay? Like file transfer has different requirements than a voice over IP call. So that's the underlying reality behind the need for QoS. And the second thing is that QoS can be described as treating each data stream according to its needs. All right, so in a nutshell, that's what QoS is. We're trying to treat each data stream according to its needs so that the users have an effective and successful experience. Okay, so when we talk about what are those needs, we can really look at 4 categories. And you're probably thinking of some. In fact, I'll pause for a second. What types of characteristics would make one service different from another? What would one service require over another? Well, one that comes up often is this idea of throughput or data speeds. So video would require much more data to be pushed through to have a successful experience than voice would. A second one, which you may have thought of, is a delay or latency. So this is the difference in time between the time the sender sends or the speaker speaks and the time the hearer hears. And so if that delay gets too long for some services, it makes the service difficult and untractable. We've probably all been on voice calls overseas somewhere, and if that delay for voice gets more than about 150 milliseconds or a quarter of a second, 250 milliseconds, you start to kind of walk on each other verbally, and it's just too much. So for real-time types of services, they have low delay requirements. For other services, like a file transfer, I don't care if it takes an extra half a second. I just want this thing to get through, and an extra half a second is fine. A third one has to do with reliability, or sometimes this is referred to in the data world in the category of packet loss. It basically says, how important is it that every bit gets there in the same place that it was when we sent it? Now you might think, well, isn't it always critical? I want to make sure that whatever I'm sending gets there exactly right. Well, it turns out that some services, like for instance voice, it's okay if we don't get all of the voice data. For instance, if we're breaking the voice into 20 millisecond voice frames and sending it out, typically cellular networks are engineered so that they drop 1 or 2 out of 100 of these frames. And we're creative with what we do when frames get dropped, and really most of the time we don't even notice it. So a file transfer, on the other hand, we want to make sure that every bit is in the same place in the received file that it was when we started. So that has a very high reliability requirement. Voice can give a bit on reliability. And the last area has to do with priority or precedence. Okay, and this is saying that for one reason or another, one of these flows has a higher priority than another flow. So if the network ever has to decide between 2 flows, it can look at the priority indicator and make the call that way. We've got to give the network something by which they can decide when push comes to shove, and that's what QoS is all about. An interesting note here, this could be priority among services that are simultaneously in service for a particular user, or it could be priority among users. I could have a platinum user who's paying a premium amount a month, then maybe a gold user, and then maybe I've got college students who just graduated, and they're on the aluminum plan, and they're saying, look, I'll pay $15 a month, and I know that I won't get the best service sometime, but just feed me when you can. And so priority could also be inter-user priority. But anyhow, so these 4 categories, throughput, delay, reliability, and priority, are the key categories we're going to be focusing on for QoS. If I could characterize a given service with respect to these 4 categories and communicate that into the network, then we could enforce the requirements of a given service so that the user has an effective experience. For more on that, we'll see you again in part 2. Hello and welcome to another session with LTE University. And my name is Russ Edwards. I'm a senior consultant at Award Solutions, and I'm also leading the effort at Award Solutions, an effort we call Technology for Business. And in this Technology for Business series, we are really trying to make technology accessible and understandable to those in non-engineering roles. And so we're trying to help people in sales and business related roles speak the language of technology in general, and in this LTE series, the technology of LTE. So this is the second in a multi-part series on LTE and quality of service, or QoS. And in this particular session, we're going to be focused on, so what does it take in order to support QoS in a particular network? So we're going to review real briefly what QoS is, and recall, if you watched the first session, that cellular networks, most cellular networks today, just treat all of the data that comes in a best effort way, and it takes the first data in and sends it out first, and it doesn't matter whether that data is very delay sensitive or requires a high bandwidth. It doesn't prioritize it in any way. It just basically takes what it gets and sends it back out again. But in fact, you could think of it like a highway, really, and that on a highway, let's think rush hour on your highway, you've got a bunch of cars that are all going the same direction, and none of them has any particular priority over any others. Well, let's say one of those cars actually had an injured person in there, and they were trying to get to the hospital. If that car was just a car like every other car, even if you're honking the horn, depending on where you are in the country, it might not mean anything, and that car will be treated like all the other cars. So what we do is we put that injured person in a car, a special white or a red vehicle with lights and sirens, and we couple that with a protocol that people know that when they see this and hear this, that they move over so that car gets special priority and special treatment. So that's really what we're doing with QoS. And so instead of everything being treated, these packets with different services in them being just first in, first out, what we're going to do is we're going to create several logical streams of information. This could be web traffic, this could be streaming video, and each stream is going to be identified with a particular quality of service, a set of quality of service requirements. Now, at the end of the first session, we talked about what these 4 QoS requirements are, and I want you to just take a brief second and see if you can remember what those 4 characteristics are. So I want you to pause me for a minute and write down those 4 characteristics, but before you pause me, let me get comfortable. All right, go ahead. All right. Well, let's see how you did. So these QoS requirements, the first one we had was throughput, or the data speeds. Okay. The second one was delay, or latency. How much delay can this service tolerate? The third one we discussed was reliability. How important is it that we get all of the data completely to the recipient that we started with? And the fourth one was priority, or precedence. Does this service inherently have a higher priority than another service that we have? So now we're going to discuss supporting QoS. What does it require to support this in a network with an illustration? All right. Let's say we have a sales organization. Let's say this is a cereal company, and they produce chocolate-coated sugar bombs. I think that's the cereal that Calvin used to eat in Calvin and Hobbes. He'd eat it every morning. And so let's say sales gets a call from Calvin, and Calvin informs them that he's just used his duplicator and duplicated himself, and now he's going to need twice as many boxes of chocolate-coated sugar bombs as he normally does. And so sales gets this call and says, okay, we're going to have to ramp up production to do this. So sales talks to production. Let's say there's a manager of sales talking to a manager of production, and they say, hey, listen, we have an opportunity to sell twice as much product as we normally do, but we need it ready by such and such a time, ready in a week, say, can we do that? And so production, the manager of production looks at this and says, yeah, no, we're going to have to, people are going to have to be working longer hours. We're going to have to fire up another line to be able to produce this, but I think we can get it done. If it stopped there, with the manager of sales agreeing with the manager of production that this is going to work, the whole process would fail, because the manager of production is going to have to communicate to everybody on his team that says, hey folks, this is what's going on. We've got to ramp up production. It's going to mean some extra hours. You know, Joe, I want you to work late on Tuesday, and Cindy, I want you to work late on Wednesday, and so forth. Unless it means we're going to be firing up another machine, you're going to be, you know, Sally, you're going to be working on line 3, and so forth. Unless they communicate this to everybody who touches this, that we've got an increased set of demands, then who cares what the managers agreed upon? All right. Now, so how does this actually apply to QoS? Well, this scenario with the two endpoints agreeing, but nobody in the middle knowing about it, is actually a pretty common scenario. And here's the picture. So let's say I've got a device, and I am talking, let's say I'm talking over a voice, a third-party voice over IP program. Maybe it's Vonage or Skype or Google Voice or something like this. So I have some kind of voice over IP. This is some kind of third-party, oops, sorry, some kind of third-party VoIP provider. Okay, and so I am reaching through the cellular network as well as data networks like the internet, and I am communicating a stream of information through this VoIP provider. Okay, unless something specific is done so that the VoIP provider somehow communicates to the cellular provider that this is a voice over IP call, it's real-time sensitive, we can give a little bit on reliability, but delay's got to be low. Unless we can communicate that somehow to the cellular provider, the two endpoints can agree that this is a VoIP call and here are the quality of service requirements, but unless everybody in the middle understands the requirements of that session, it doesn't matter what the endpoints agree. Now this scenario that we're talking about is often called OTT, or over the top, where basically the application, in this case voice over IP, is using the cellular network and other networks as just transport. Some people call them dumb pipes. Sometimes it's a little bit derogatory, but they're trying to use these networks just as transport and provide the applications on top. The issue with that is, how is the cellular network going to be able to take action to make sure that that voice over IP call is treated well? It doesn't even know, unless real special efforts or measures are being taken, it doesn't even know that is voice over IP traffic. So it's just sending things as a best effort, in a best effort manner down there. And if push comes to shove, it's possible that the voice packets could get deprioritized and that service could get disrupted. Okay, so in order for QoS to work, what is required? Number one, the QoS requirements must be communicated throughout the process to all critical nodes. Everybody needs to know that this is a real-time video service, say. And if it's, let's say it's a video and it requires a high bandwidth, maybe they reserve the bandwidth so that they know that, yeah, just because I can support it now, I still need to make sure that I'll be able to support it 10 minutes from now. Okay? And then the second thing is, so we'll underline this and say we need to communicate the requirements. And second, the critical nodes must be able to enforce the requirements. In our example, if the production manager turned toward one of the people on the line and said, okay, say one of the people managers there, and said, okay, you're probably going to need to work overtime for this. If this manager is not does not have the authority, is not enabled to get people to work overtime, then where is this going to go? So those two things, we need to communicate the requirements, and we need to make sure that every critical node that touches this data has the ability to enforce those particular requirements. Okay, those two things are required. All right, so that's it for this session. In the next session, we're going to put these pieces together, and we're going to talk about enforcing QoS in LTE with a services framework you may have heard of called IMS, or the IP Multimedia Subsystem. We'll see you next time. Again, my email address is russ@awardsolutions.com. If you have any feedback or questions or ideas for other sessions you'd like to see, please send me an email. We'll see you next time. Hello and welcome to this LTE University session on QoS and LTE QoS with LTE and IMS. My name is Russ Edwards, and I am a senior consultant at Award Solutions, as well as I'm currently leading the Technology for Business effort at Award Solutions to help make technology, to help those involved in sales and business-related roles speak the language of technology. And in this series, we're focusing specifically on the technology of LTE. So this is the third in a multi-part series on LTE and QoS, and specifically we're going to be talking, as I mentioned, about QoS with LTE and IMS. We're going to be starting to pull some of these pieces together. So in the previous sessions we learned that different services have different requirements, and we talked about, and that QoS is, what QoS really is treating these services according to their requirements. And so in the last session, we found that in order to make QoS really work, we have to have a mechanism for doing two things: communicating the particular requirements of the session and enforcing. We need to make sure that all the critical nodes have the authority to and some ability to enforce the particular QoS requirements for a given service. Now we're going to pull the pieces together a little bit and say, okay, now let's talk more specifically about LTE and how this would work in LTE. And we're going to do this in the framework of something called IMS, the IP Multimedia Subsystem. Okay, the IP Multimedia Subsystem. Now, the reason that I am coupling the two, and LTE will work fine without IMS, but the reason that I'm coupling the two is that most of the operators that are either have deployed LTE or are going to deploy LTE in the near future are looking at deploying IMS as well. So this is a common scenario. And what IMS really is, it's a services framework, a standardized services framework for providing IP-based communication services. So if we want two endpoints to communicate over some kind of IP-based connection, IMS is a good standardized way to do that. It's obviously it's possible to have them communicate without IMS, but as we say, a number of folks deploying LTE are going to be using IMS for this. Okay, so if this, we'll do another cloud. If this cloud is our IMS network, it's a collection of servers and functions that help enable the connectivity of these endpoints that we have. And one of the things that IMS is really good at, and it was designed into IMS, is the ability to communicate the quality of service requirements for a session. And so we can communicate that this is a video session and it's going to require, say, 300 kilobits per second. And the delay needs to be this short, for instance. So IMS is really good at saying, okay, party A, what is it that you want to do? And party B, what is it that you're able to do or what that you can do? And so A, for instance, could invite B to a video call, and then we could check, the IMS system could check with B and say, okay, you're being invited to a video call. Here are the parameters of the call. What do you think? Okay. Now, so let's say you have a cellular service provider who has rolled out LTE. Okay. So a particular user, let's say user A, sets up a data connection with the LTE network. The way this is going to work, if this operator has deployed IMS, we're going to set up a data connection over LTE, and then we're going to have another connection, connectivity through the LTE network into the IMS network. So once user A has LTE connectivity, then it's going to send a request to the IMS network to invite B to a particular video call. So then we can have this negotiation about what are the requirements of the call. We're going to reach out to B and say, what do you think? Are you able to do this? And then, if that's all that was done, if A and B agreed on the requirements of the call and said, okay, let's do it, and that's as far as we went with it, this would be what we call the over-the-top scenario, like we spoke about in session 2. Right? The cellular network would have no specific knowledge about what this particular session required and would have no way of specifically supporting those requirements. All right? So what we need is some way for IMS, some server in the IMS network, to communicate to the LTE network. Here are the requirements of the call. And one of the ways we can do this is we can stop the IMS setup at a particular point. We suspend it and say, all right, let's go check and make sure that the access network that we're working with, in this case LTE, that it has the ability to support what we're trying to do. So there's a special function that is added as glue here. It's called the PCRF. It's easy, as you know, to get lost in the acronyms, but it's called the policy and charging rule function. The main thing is, it in essence is a QoS. In this case, is being used as a kind of a QoS communicator and interpreter in some sense. So what happens is that IMS is going to send this function the requirements of the particular call that we're setting up and say, what do you think? And can the network support it? The PCRF is going to take those requirements and communicate them, communicate them in a format that the first node in the transmission of this data can understand. So in the LTE network, there is a node. It's like a gateway node that communicates with a packet data network, and in this case, it's the IMS network. So what do you call a gateway node that communicates with a packet data network? Well, we call it a packet data network gateway, okay, or a P gateway. All right, so that's what this thing is. It's a P gateway. And so it's going to be taking the incoming packets for this session and sending them back through the LTE network. So what happens is this PCRF communicates the QoS requirements in a format the P gateway knows how to understand. Okay, so it does perhaps does a bit of translation in there and communicates this to the P gateway. Then the P gateway then takes it, and there are other nodes in the network. And here we've got an LTE base station. You may have heard the term eNode B or ENB. That's what we call the LTE base station. And so the P gateway communicates to these other nodes. In fact, I'll write the names in there for the nodes in case you're familiar with them. Otherwise, it's probably not that important that we go into too much detail. But then we end up communicating the requirements for this session to every critical node that's going to be handling this data traffic. And it culminates with a communication down to the actual eNode B, the base station that's going to be transmitting it over the air. And so each of these, this is the communication component where each of these nodes becomes aware of the QoS requirements of this particular stream of information. Now I want to zoom in on the eNode B for a minute, because if you think about it, this eNode B has a lot going on, because it's not just one user that we're supporting here. We've got multiple users here in the network, and so what happens, there are buffers at the eNode B, and the eNode B has a buffer for each of these users. Now, if we were just handling this on a best effort, from a best effort approach, then we would not have any information to treat one stream of information any differently from another. But in this case, because we've already communicated the QoS requirements, the eNode B could know, for instance, that this pink user is doing voice over IP. And voice over IP is not a high bandwidth service. It doesn't take a lot of bits per second to communicate voice, but we do need to make sure we're getting a lot of little bits regularly, or we're going to have interruption. If there's maybe this blue user is doing web traffic, and for web traffic, the delay, we're not so concerned about delay, but we want to, if somebody clicks on a link, we want to feed them as much of that web page as we can, as quick as possible, so it's a nice experience for them. So it's very bursty, it requires high bandwidths, but not so delay sensitive, and doesn't have to be regularly scheduled. Okay, there could be video. And I've drawn these in different users, but keep in mind that the same user might be doing some kind of video and doing some kind of web or email session at the same time. So these could be different services going on within the same user's device at the same time. And in that case, the eNode B still keeps track of them as part of different streams. Okay? So when push comes to shove, and I'm trying to serve at, let's say this is a video user, this green one, is a video user, and they need a lot of bits regularly, and then the web user requests a web page, the eNode B looks at this and says, boy, I got all this data to send to this web user, what should I do? And it looks at the QoS requirements and says, no, this is video, streaming video, we need to make sure we keep a lot of data going down fairly regularly, so I'm going to make sure that's the big rock here, that's scheduled in, and then I fill in the gaps with the web traffic that is more flexible. Okay, so the point here is that through using IMS, combining IMS, which is good at communicating, agreeing on the QoS requirements, and introducing this node, the policy and charging rule function, that lets the IMS network communicate the QoS requirements into the LTE network. And then, by designing the LTE network in such a way that those QoS requirements are propagated down all the way to the eNode B, we can help ensure that all of these services are treated according to their needs, which is the definition of QoS. All right, I hope that was helpful. If you have ideas on this or questions on this or ideas for other sessions, my email address is russ@awardsolutions.com. I'd love to hear from you. We'll see you next time. Hello, my name is Russ Edwards. I am a subject matter expert with Award Solutions and LTE University, and I focus on an area of the business at Award Solutions that we call technology for business. You can see that down here. And in the technology for business line, we endeavor to help those involved in sales and business related roles speak the language of technology without having to design it. And so today's session is going to be the fourth part in, I think, what will be a 4-part series. Originally 3-part, but we decided to extend it. The series is on LTE and quality of service. And this portion is going to deal with how LTE supports quality of service over the air. Now this session is going to get a little more detailed than the previous sessions, but I think you will find it interesting. If you hang in there with me, you will leave this session with a greater understanding and confidence in LTE's ability to support quality of service. So let's jump right in here. What we're going to be looking at in this session, if this is the LTE base station, and you may know that that's called the E node B or ENB sometimes. And this is an LTE device, sometimes called the user equipment or the UE. The E node B has to manage a number of different flows for different subscribers that are active in its coverage area at any given point. Okay, so this might be web traffic for one particular user. This could be voice over IP for somebody else, and maybe we're even doing video here for somebody else. So I have these different mobiles, or different devices, and as the E node B, I need to make sure that everybody gets served in a way that gives the users a rich experience for what it is they're trying to do. And as we've spoken about in the previous sessions, and by the way, if you haven't watched the previous sessions, I'd recommend that you stop here and go watch the previous sessions to help fill out your understanding of QoS and how LTE supports it. But we saw that the definition of QoS was that we were trying to support each service, different services, according to their needs. And we said that in order to do that, we had to do a couple of things. Number one, that we had to be able to communicate the QoS requirements for a session, maybe the data rates, the how tolerant it is of errors, how much latency or delay it can tolerate. So we had to be able to communicate the QoS requirements for a session to every node that's going to be touching this data, okay, this flow of data. The second thing that we need to do is every node that touches the data has to have the authority and the ability to enforce that particular QoS for that stream of information. So what does this mean when we get to the E node B? Well, what it means is that as the data is coming down, let's say we've got this web traffic that's coming down from the network, we need to be able to classify that as web traffic and know what its QoS requirements are, and then send it over the air in a way that matches those requirements. Probably a better example would be if this is voice traffic, voice over IP traffic that is provided over the air, or I'm sorry, that is provided to the E node B. We need to be able to know that in order to support that voice successfully, we have to keep the delay as short as possible, and we need just a little bit of data. It doesn't take a lot of data to support voice, but we need it regularly. Okay, so we're going to see how the E node B deals with these different requests and how it can manage the differing QoS requirements that it has going on at any given time. Now, in order to understand this, we need to lay a little bit of a foundation, and I find it helpful to think of a radio, just an AM radio. And so if you picture your AM radio dial, if they even call them dials anymore, the AM radio dial is going to go from somewhere like 520 kilohertz up to 1610 kilohertz. So when we listen to the radio station, we might have a radio station we like at 850. Okay, so what happens is we've taken this band of frequencies that have been allocated for AM radio, and we've broken it up into different frequency channels, and then a given radio station has been assigned a frequency channel to use. So as a result, this could be some sort of talk radio that we enjoy listening to. This one could be sports. And then up here we have, favorite hits of the 70s, 80s, and 90s. So as a result, we've got all these different radio stations. Each one occupies a specific channel or a subset of that band of frequencies that we have. Now you may know that LTE is based on a technology called orthogonal frequency division multiplexing, or OFDM. Those of you familiar with the cellular industry know that in our 3G world, the technologies are based on CDMA, code division multiple access. Think of OFDM as the counterpart of CDMA. The 4G systems, instead of being 4G systems like LTE and WiMAX, instead of being based on CDMA, they're based on OFDM or OFDMA as a result. So that's how those two compare. And OFDM, by the way, is not new. We've been using it for years in technologies like Wi-Fi. All right. So what OFDM does is it takes a band of frequencies and it breaks it down into multiple, what we call subcarriers. Okay, multiple channels, much like we did with the radio station. And then each of one of these channels can carry a certain set of bits. We send them over each channel, just like we're sending a radio station in the radio analogy. Okay? So what's going to happen is that when a user needs data, we are going to assign a user a set of channels that will carry that user's bits. Okay? So 12 subcarriers. We're going to combine these together. It's kind of like sushi in a sushi restaurant, right? You get the whole roll. You can't just get one little piece of sushi. You get the whole roll. That's what's going on. We never assign just one subcarrier or two subcarriers. We wouldn't get enough data to really make that worthwhile. It's a minimum of 12. But the point is that we give one user a block of subcarriers based on what they're trying to do, and another user a different block of subcarriers, maybe multiple blocks of subcarriers, to do what they want to do. All right, so this could be assigned to user 1, and user 2 could have a bigger block of subcarriers, okay, to do what they need to do. So you're starting to get the picture for what this activity at the eNode B might look like. And in order to see what this how this goes, let's look at this matrix. It's a matrix of frequency and time. We've got time here on the horizontal axis, and we've got frequency, okay, on the vertical axis. Now, what we do is we create this matrix of time versus frequency. And on the frequency side, this is one of those, we'll call it a block. Okay, it's a block of those 12 subcarriers, those 12 frequencies that can carry data. Okay, so on the frequency scale, the eNode B has a set of blocks that it can assign to users as the need arises. Now, one of the neat things about LTE is that LTE can be deployed in different amounts of spectrum. There are 6 different amounts of spectrum that if a wireless operator only has 1.4 megahertz, you can deploy LTE. And then 3 megahertz, 5 megahertz, 10, 15, up to 20 megahertz. You can deploy LTE. Now this works a lot like water in pipes. The larger the frequency band you deploy, the more data you're going to be able to carry through that. Just like the larger the pipe is, the more water you're going to be able to get through that. And so an operator deploying LTE with a 10 megahertz band is going to be able to get a lot more data through there than an operator deploying LTE at 1.4 megahertz or 3 megahertz in a 1.4 or 3 megahertz band. Okay, so depending on how big your band is that you're deploying LTE in, that dictates how many of these blocks that you are able to assign. We're seeing a lot of operators in North America. I say a lot, you know what I mean. deploying LTE in 10 megahertz. Okay, what that means is that in 10 megahertz you can actually get 600 of these, what we're calling blocks. Okay, so we can call this one block 1 and this one block 2 and so forth up to block 600. Okay, so on the time, that's the frequency scale. On the time scale, we divide the time axis up into 1 millisecond segments. Okay, every one of these is 1 millisecond. Okay, so now let's do a little math. So this becomes the scheduling map, really, for the eNode B. So if you think about this, I've got 600 blocks from a frequency perspective, and that I can use, and in a second, given that I've got these broken into little 1 millisecond segments, that means I've got 1,000 of those segments every second. So I've got 600 frequencies, or 600 blocks, that's better, times 1,000 of these every second. That gives me 600,000 blocks that I can, these are resources that I can schedule every second. Okay, so this is the view of the world from the eNode B. So now let's say that somebody wants to do a voice. Okay, they want to do voice over IP. Voice over IP, as we said, doesn't take much bandwidth, but you need it regularly. So maybe I could give the user, assign the user one of these blocks for 2 milliseconds. Okay, basically, in order to support voice, you would need to do that every 20 milliseconds, and that would be enough to get enough data down there to support a successful voice call. Okay. Now, of course, there are other variables and so forth that we're not complicating things by looking at how many bits can be carried in a particular resource. That varies based on your radio conditions and other things. But so you get the idea. That's how we would support a voice call. If somebody wants to do video, well, we know that we're going to have to use maybe 10 times the blocks or 50 times the blocks in order to do video. And it also is going to need to be able to be scheduled regularly and so forth. And we'll just do it like this and save a little time. Okay, so with video, we use more blocks for longer periods of time, and that helps us get enough data down there to have successful video. Well, what about web traffic? Well, the great thing about web traffic is that it's not so delay sensitive. Right? Somebody waits an extra second or a half a second for their results, not a big deal. Okay? So what we can do with the web traffic is we can fill it in here in these gaps that we have. And if we have a lot of extra resources available, the beauty of this is we feed those users. We get that web page down to that user very quickly. And if you have a 3G device, like I do, sometimes it's not quite as quick to get the web pages as we kind of wish that they were. Well, in this type of scheme, if the resources are available and not being used, we can just allocate those to the user, give them big blocks of bandwidth, a lot of those blocks, for a period of time that we have, and just evacuate the data from our system. That frees up the system to serve other requests, and it makes the user happy because they got their data in a very expedient fashion. All right? So I hope that gives you an idea for how LTE actually incorporates this mechanism to be able to physically support quality of service over the air. That concludes this session. I hope it was helpful. I'd love to hear from you. Again, go back to the top here. My email address is russ@awardsolutions.com. If there are other topics that you would like to see covered here, I'd love to hear about them. Otherwise, have a great day, and we'll see you next time.